Thanks everyone. Thanks for joining on a Friday afternoon for a talk, Underground. I'm really excited to present some of the work I've been thinking about. So kind of the way I'm going to tell the story for this talk is I'm going to start with this observation that's been made by many who've done robotics or AI research, but often attribute it to Moravec, which is that we often notice that it's been historically harder to get robots to do things that we take for granted as humans, like motion through the physical world, perception, manipulation, than it has been to learn how to do things that involve reasoning or symbolic manipulation, like solving math problems or chess, right? And so, yet, I think in recent years we've seen tremendous progress in the ability of robots to perform at least very narrowly scoped manipulation tasks. An example of this is one of my students, Tonghe. He's doing a short folding demo, which has now become kind of almost cliche in our field, but I think which even 3 years ago doing from pure learning would have been rather surprising and incredibly impressive, right? So, the technique he's using for this is he's collecting data with a bimanual teleoperation device, as many of you might be familiar, using that to train a policy based on the teleoperation data to perform the action. And this approach, often called behavior cloning, it's not very new. It's been around, I think, since the late 80s, kind of motivated by early self-driving efforts. And then more recently, in the early 2000s, there was sort of a renewed interest in using these techniques for things like robotic manipulation. But something happened around 2023 where we saw this inflection point in the capabilities that we could acquire through behavior cloning. And that resulted in a wave of kind of industrial interest in scaling these techniques towards kind of more ambitious projects, form factors, and greater land of diversity. So what I'm going to try to ask in this talk is, what is the thing that caused this inflection point? And before going further, I'm going to give one obvious answer, which is that obviously we started collecting more data. And maybe you could call this the pragmatic Moravec paradox, which is just simply getting data for the things that we do every day has historically been more difficult than getting data for symbolic tasks where we have like internet scale repositories. But I think in addition to this, there were a couple key algorithmic breakthroughs which kind of emboldened us to start collecting more data and enabled us to learn better from the data that we collected. And so what I'm going to argue is that this is sort of an algorithmic Moravec paradox, in the sense that unless certain algorithmic interventions are undertaken, it's going to be very difficult to learn from the data that we collect. And these algorithmic choices are precisely the things that enable database scaling. Right? So in this talk, what I'm going to try to do is provide some mathematical evidence for this algorithmic Moravec paradox view, demonstrating why learning from demonstration in areas like the physical world can be fundamentally more difficult than in symbolic reasoning settings. And then finally trying to understand how how the key breakthroughs introduced in sort of this inflection point, they mitigated the fundamental challenges that we bring up. Right? So that's going to be the point. And finally, there will be a lot that we still don't understand. So just so you know what those key breakthroughs are, many of you might be familiar with them if you do practical robotics research. So one of them is the practice of action chunking. So action chunking is the somewhat counterintuitive practice where rather than running your neural control policy at full frequency, you'll predict a bunch of actions in sequence and execute them in open loop, or a chunk of them in open loop. And I think many of us recognize that action chunking has been a foundational innovation that underlies a lot of the capability of today's models. And the second intervention is that of the generative control policy, which basically uses a generative model to predict the distribution of control actions with the intention of modeling, for example, bifurcations or multiple modes in the action distribution. Right? So training policy to predict these distributions. So these will be the two interventions that we study. Okay, so kind of the unifying kind of perspective that we're going to have is that we can think about a lot of these interventions as sort of reparameterizing the closed loop dynamics between the robot and the learner. And by doing this reparameterization, this actually puts us into the regime where scaling in the bidder lesson now becomes effective and possible. Right, so I'll try to make that claim throughout the talk. So the first thing I want to convince you of is sort of, why is this learning from demonstration tasks so difficult in continuous control settings like robotics? What's unique about robotics? So we're going to use an MDP formalism, right? So many of us might be familiar. So states are represented by S, actions by A. We can transition to new states by some transition probability. We have rewards, which are functions of state and action. And finally, some distribution of initial states. In addition to this, we're going to also have some problem horizon, right? The number of steps that we're going to take, and that will be a key object in some of the results that we present. So we're going to be studying policies. Policies are just ways of describing an agent's action in an MDP, focusing for now on Markovian policies, those which map states to distributions over single actions. And of course, this can be true in robotics as well as in sort of language modeling settings. You can view both as sort of policies. And finally, our desideratum is that of maximizing expected reward. So we'll have some reward function, and what we care about is how much reward the policy accumulates under the distribution it induces. So specifically, we draw states from our initial distribution of states, we execute the policy to give us actions, we get new states from the transition, et cetera, et cetera. So this is the thing that we kind of optimize. Okay. So the behavior cloning paradigm, it takes place in the protocol of offline imitation learning, oftentimes called learning from demonstration. So in learning from demonstration, we envision that our data is collected by an expert, which itself can be described by a policy pi star. So the expert collects n IID trajectories coming from this distribution induced by the expert policy. And finally, given these trajectories, I run some algorithm, and that algorithm produces a new policy pi hat. And pi hat is supposed to have the property that its cumulative reward is close to that of pi star. So for example, the suboptimality is less than some number epsilon, which is shrinking as I collect more data, as I collect more trajectories. So one way of accomplishing imitation learning is via the behavior cloning algorithm, where pi hat just minimizes some notion of supervised learning error. Right? So for example, I'll take my expert data, I'll specify some loss function, which will be dependent on the way that I describe my policies. For example, mean squared error could be a score matching loss. And finally, I'll optimize this loss function over all policies in some reasonable class of policies. For example, this might be by doing gradient-based optimization on some given neural network architecture that I've pre-specified. Right? So this is the behavior cloning algorithm. And why do we like behavior cloning? Well, supervised learning just works really well in machine learning, both historically and theoretically. Right? So we know, for example, that if you train on some distribution, your test error on that same distribution is typically bounded by generalization error, which we typically expect to get smaller and smaller as we collect more data. But the fundamental question in behavior cloning is not the generalization on the training data, it's actually the mismatch between BC error and the cumulative reward. Right? Just because we match our demonstration data doesn't necessarily mean that our cumulative reward is too small. So in a little bit more detail, when we do behavior cloning, we're essentially minimizing the fitting error, but anchored at every state that we see in our training data. But what we care about when we evaluate for reward is the policy rolled out on its own generations, which can cause errors to accumulate in small amounts over time. And this is often called the cursive horizon. Right? The distribution we care about is the one induced by the learned policy, not the one induced by our expert data. So now we can ask ourselves, like, what's the right perspective to understand compounding error in this setting? And one way to think about this is to think of robot learning as a control problem. Now, what makes something a control problem instead of a general MDP? There are many answers. One of which I find useful is the perspective of stability. So roughly speaking, there's a quantity called stability. It's basically refers to the sensitivity of a system to perturbations of its inputs. And it makes it's very usable in sort of continuous control settings. Right? So we'll be in a continuous control setting here where, for example, our dynamics are going to be deterministic but smooth, and our policy is going to be deterministic and smooth. And stability will just measure the sensitivity of the system to perturbations of its inputs. And we'll describe this in more detail later on in the talk. So in particular, there are a bunch of different scenarios in which you may or may not have stability. One is open loop stability. So open loop stability informally just means perturbations of the inputs to the dynamics, right? And sort of open loop incremental stability, the definition we'll work with, is where if I make a perturbation to the dynamics, I have an exponentially fast contraction back to what I would have gotten had I not had one. Now similarly, I can define closed loop stability, where now I define stability based on the closed loop dynamical system. So this is a system which takes the regular policy and considers what would happen if we added perturbations to the policy's action on its own state, and I can define the same thing. Now finally, an issue that can arise is closed loop instability, specifically of the learned policy, where small perturbations tend to accumulate quite massively. So the question we're going to ask then in terms of stability is, how does test time error arise? And essentially the key difficulty that we can show is that in fact, even if the expert and if the dynamics are both stable and open and closed loop, it may be the case that the learned policy induces instability. Okay. So let me describe how this happens. I'm going to state a negative result. And to state the negative result, I'm going to try to convince you that it's in the nicest possible setting that this result could hold. So I'm going to consider the following. The learner is given a set of possible pairs of policies and dynamics. Each pair of these is smooth, is deterministic, is Markovian, meaning that just that every action of the policy depends on the current state, and the transition only depends on the current state. And lastly, that they are stable, in the sense described earlier on, specifically that that errors are forgotten exponentially quickly, both in open loop and in closed loop of the expert. Okay. Right. Finally, I'm going to tell you that the learner is promised that the true policy and the true dynamics lie in this set that I've constructed. So they abide by these properties in this set that I know. Okay. So we can try to think of these three conditions as specifying a really nice behavior cloning problem, one that has all the properties that we might want. Also, all these pairs pi and f are one-step controllable to make it even nicer. Okay. So the last condition is one we're going to restrict one way we're going to restrict our algorithm. So we're not going to tell you what the algorithm can and cannot do in terms of how it's run. We're instead going to restrict the kind of policies the algorithm is allowed to learn. So what we're going to do is say that the learner must return policies which are smooth, which are Markovian, and which are deterministic. In fact, you can remove the deterministic condition, but it just changes things a little bit, makes them more complicated. Now, why would you impose these restrictions? Well, because smoothness and Markovianity just enforce that you have to match the expert distribution, right? You just have to be basically, your expert policy cannot be much more expressive or less expressive than the expert. So let's now understand, under these conditions, how easy it is to imitate. What we're going to study is just learning in the square loss, which is kind of a very natural and classical style of loss that you might consider. And we're going to consider behavior cloning in this loss. Now, this is in contrast to kind of more traditional analyses of behavior cloning, which have used the 0-1 loss, if you read the classical papers by Drew and Bagnell. And we're going to use the square loss because when we have continuous action space, we cannot get actions perfectly correct. Instead, we're going to have to use something that allows for some degree of tolerance. And it turns out this is actually really important. So now let me tell you the negative result. The negative result is that there exists a set of policies, or rather I'll say it this way. Fix any scaling law, so any rate of decrease in your error that you would like, n to the minus alpha for any alpha. You can construct a set of policies and dynamics abiding by what we found on the previous slide, which satisfy all the niceness assumptions of smoothness, stability, etc., which have satisfy the following conditions. So the first is that if you do supervised learning on the square loss, your error is going to decay like the scaling law. Right? So from a supervised learning perspective, generalization is not a challenge. However, any algorithm that satisfies the smoothness and Markovianity restrictions, right? Any algorithm that returns policies that are not much more expressive than the expert, this is going to satisfy an exponential in horizon compounding error. It's going to satisfy this. Now, you might ask, is this just about behavior cloning? No, it's not. It applies to every algorithm that just uses the demonstration data. And in fact, even if the learner knows the reward function, they cannot do better. So in particular, algorithms based on offline reinforcement learning are going to be unable to circumvent this lower bound. So why does this happen? The answer is actually about control theoretic stability. So we can construct an instance where two pairs of policies and dynamics agree on one subspace and are indistinguishable. And what you can show is that despite this, there might exist an orthogonal subspace where any policy which agrees with the data on the vertical axis, which stabilizes one of the dynamics, will destabilize the other, and that this is unavoidable. And we can embed this construction into kind of a more general one that makes us sort of robust to maybe certain things that would arise in just linear cases. So this is kind of what's going on. You basically have this kind of irresolvable tension between fitting the data on, or fitting the dynamics on one data distribution and sort of stabilizing that which you didn't see from being demonstrated. Okay. Now, we can also compare this to what we see in, for example, discrete settings, right? Discrete behavior cloning settings. So, for example, in discrete regimes of behavior cloning, we often see that we only have polynomial and horizon compounding error. And the reason is because, essentially, if you either make a mistake or you don't, then the probability of mistakes adds up linearly. Whereas when you have a control system, the effect of mistakes can add up exponentially. Hey, Honkai. Cool. So essentially, I'm billing this result as the quantitative Moravec paradox, basically a formal mathematical separation between learning in the continuous control world versus learning in the discrete world, even in the nicest possible continuous control system. Cool. So let's now go into describe some of the interventions that enable us to circumvent this challenge. So this is work led by Thomas Zhang. He's a PhD student at University of Pennsylvania. So again, as I mentioned, the action chunking innovation is regarded as one of the foundational innovations. It was developed both at one lab at Stanford and one lab formerly at Columbia, now also at Stanford. And essentially what we do is instead of predicting a single action every time we make an observation, we predict long horizon sequences of actions. And one way to think about what action chunking is doing is it's actually removing the restriction that the learned policy is Markovian, right? Because when I do action chunking, I'm implicitly correlating my actions across time by committing to an action from stale observations. So how might we learn action chunking? Well, if we're in the traditional behavior cloning world where we're using square loss regression, we would just simply add an action chunk step index to our policy and train our policy to predict a vector of actions starting from the current one all the way through the chunk. And we would optimize this. Now what you can prove is the following, that if you do this action chunking intervention, and if your dynamics are stable, both in open loop as well as in closed loop, then for all chunk lengths that are sufficiently large, you avoid compounding error. You just pay for some constant C star. Now you might ask, what is K star and what is C star? Am I just halving the horizon or shrinking the horizon? No. C star and K star are absolute and horizon independent constants that are polynomial in relevant problem factors, specifically factors that depend on stability parameters of the system, as well as like smoothness constants. And finally, this effect is not just increasing action chunks to eat up the horizon, it actually just saturates at a critical K star and ends up being horizon independent. Right? So it's really a qualitative change rather than a mitigation of problem horizon. So why does this work? Well, let's see what happens if we don't do action chunking. Right? As we saw previously, we might just become susceptible to compounding error. Now, if we do action chunking, we're not going to get compounding error on the first action chunk because we've supervised on that action chunk. Right? So that's going to be okay. Right? And because we're open loop stable, the small amount of error we do make on the first action chunk will keep us close to the nominal policy. Now, what about the second action chunk? Well, let's consider a thought experiment. Let's imagine instead that the second action chunk is reset to the perfect state that my expert would have visited. Okay. So the key finding we can prove is that if the learned policy is Lipschitz and sort of satisfies some other reasonable assumptions, and if the chunks are large enough as a function of the open loop rate of contraction in the dynamics, then this learned policy pi hat is itself going to be closed loop stable. So what does that mean for us? It means the following. It means that if the policy is stable, then its own actions that it takes will track the imaginary actions it would have taken at the reset state, because it's going to be somewhat stable to this perturbation from where it was here to where it was here. So if we wait long enough, you'll have this contraction. And you'll get this, if you take a long enough action chunk, this contraction will contract exponentially, moving you back to the next set of states, and the process can repeat. Right? So this is sort of what action chunking, you can think of action chunking as doing. So this is actually consistent with a lot of our visual observations of what action chunking does when we use it on a robot. We see that if we don't action chunk, we have a lot of jitteriness because we're picking up instabilities in the learned neural policy. But if we action chunk, we see a lot more smooth trajectories because we're not exacerbating those instabilities. Right? Now, we might ask, is control theoretic stability actually the thing that's driving action chunking in experiments? So we wanted to run a controlled experiment for this. So what we're going to do is we're going to train a state-based regression policy from a deterministic expert. So this removes issues of multimodality, it removes issues of partial observability, it removes issues of high-dimensional observation. And we're going to plot both the success rate against how many steps of action chunk we evaluate, as well as how many steps of action chunk that we train on. So the color depicts how many actions are used for supervision, which might capture things like representation learning, denser feedback, and the x-axis captures the length of the action chunk. And what we can see is that indeed executing longer action chunks seems to be very salient for performance. It's not simply by supervising on longer ones. So this seems to confirm our hypothesis that indeed it's the execution of the long action chunk that induces the control theoretic benefits. And in addition, that action chunking has these benefits that persist even above things like representation learning, partial observation, or imitation of receding horizon control. So you can actually interpret the last slide as an imitation of RHC. Right. Now, that's not to say that representation learning and partial observation don't play a huge role. They certainly do. But we can see these benefits of action chunking even in the absence of those difficulties. Now, you might ask, why am I assuming my dynamics are open loop stable? And what I'll say to this is, in fact, action chunking came alongside another design decision in robotics, which tries to make the dynamics as stable as possible. So robotics frequently uses position control to put us into the regime of open loop stability. Right? That can be at the end effector at the joint level, but it is position control. right? So what we're doing, at least in kind of low data regimes, is position commands are being executed, and then a closed form, high frequency controller is tracking these positions, right? And so, in fact, the open loop system, we can view the open loop system as precisely just a system that designates these waypoints, and we rely on the low-level controller as sort of reparameterizing our dynamics. So kind of the way to think about this then is to say that the action chunking innovation is really about reparameterizing a control system. It's about taking a control system, which might be unstable if we use raw torques to joints, making it open loop stable if we use end effector control, but because of our negative result, this is still prone to error in behavior cloning. And then finally adding action chunking as one final layer, which makes the open loop stable system finally error resilient under learning. Right? So that's how we can think about it. Now, do we need action chunking? Maybe many people in the audience might be interested in this from practical view. And what I would say is well, you can think of action chunking as being certainly beneficial in that it sort of slows the policy to prevent instability, and that it can also address most forms of instability related to the embodiment itself. But action chunking is not going to fix instability in the broader environment, and kind of my sort of vibe conjecture is probably with enough data, you can probably get rid of it. But at the very least, in the low data regimes that encouraged us to start scaling at the inflection point, action chunking was indispensable. And probably at small scales, it still is. So, as I mentioned, what happens when the closed loop of the object that we're manipulating and the embodiment is not stable, right? What do we do in cases like where we have like a string, where we have slippage? How are we going to handle this? Certainly action chunking is insufficient. So what I'm going to argue is that the second intervention, that of generative control policies, is actually aimed at intervening on potential instability in the dynamics themselves. And I'll explain how we get there. So this is led by Chao Yipan. He's a PhD student at CMU, advised by Guanyi Shi and Guanan Gu. So let me explain the traditional motivation for why we would use generative models as control policies. So it was believed that as we started to scale up robot data, we would collect data that demonstrated multiple strategies for solving the same tasks. So for example, a robot would be confronted with an obstacle. The robot might be able to choose to go above or below the obstacle. This would result in two modes in the data distribution, and that one would need some policy that was sufficiently expressive to mimic those two modes in the data distribution. So what we figured is, why not use a distributional function approximator that can train the conditional distribution of actions given observations from these sorts of policies. Right? That was what was believed. And sort of one of the early innovations was to use a diffusion-based policy. These have kind of switched over to flow-based policies. And this generative control policy, these are the basis for essentially every large-scale robot policy that's being trained today. And in fact, they're also very theoretically powerful. One can prove that indeed, if you do the right control theoretic low-level tricks, they can imitate arbitrary distributions of expert data. And I think even to people who are on the periphery of robotics, I think they would credit generative control policies as the technology that's really responsible for much of the robotics revolution, though maybe people that spend a lot more time with robotic behavior cloning would also give action chunking equal weight. Right? So really, what are we doing in a generative control policy? Right? Essentially, we're just taking the behavior cloning problem and we're replacing this loss with a distribution fitting objective. The one I'm going to focus on today is that of flow matching. So flow matching learns a velocity field which tries to transport Gaussian noise Z to a distribution over actions. It's trained by some denoising objective, and it's executed by doing inference where we start at some Gaussian noise, we flow forward our ODE in time, and at time one we get an action which we deploy in the system. So the question I'm going to ask is, are these generative control policies, are they really about multimodal distribution matching? Or are they secretly doing something else and something more significant? Okay. So what we try to do is develop a kind of a taxonomy of what are the different aspects that are bundled together when we use a generative policy like a flow policy. The first is certainly distributional learning. This is the reason that they were motivated, right? Capturing modality of the data. The second is that we also add noise during training. We can call this stochasticity injection, right? So we add this noise variable Z, and this is this seems to be quite useful. And finally, the last thing we can see is that a flow model uses multiple steps to generate its actions. We can call this iterative computation, right? So in practice, I take my flow, it's a continuous time object, I do an Euler discretization, and I use that to generate actions. Now, in a little bit more detail, the iterative computation is not just performed at inference time, it's also supervised during training. So our flow matching objective supervises our denoising process around every step of this action prediction, not just at the final steps, and that seems to be quite salient. Okay. So what we can ask ourselves is which of these components are actually salient for learning? Is distributional learning really important? So we started off by comparing policies trained with flow matching to those trained with pure regression. Importantly, unlike a lot of past comparisons, we controlled for the policy architecture. So it turns out that the people who invented diffusion-based policies were also really good at deep learning, but maybe not so good at benchmarking the same loss function on the same architecture. So it turns out if you control for architecture, here flow policies are represented in blue, and regression policies are represented in gray, normalized so that flow policies always have success rate 1. And the red dotted line represents those tasks on which flow policies do, or which regression does less than 95% success of the flow policy. So you can see that you only dip below 95% relative success on a handful of tasks, right? Moreover, those tasks often don't even seem to have complicated observation modalities. They're just a couple of state and image. There are many observation modalities, from VLA backbones to images to 3D point clouds, but regression and flows are basically doing the same. So it doesn't seem to be that this is a universal phenomenon, and it doesn't seem to be that it seems to be something that's concentrated in a couple regions. Okay. I should also mention that this is for single task learning, right? Multitask pre-training might have totally different dynamics, and you should take this with a grain of salt. So now what we can ask is, what are the tasks where we do see the improvement? Are they ones that we think we have a lot of diversity in the data we collect? Are there ones where they have a lot of multimodality? It doesn't seem that way, just looking at the tasks. These are rather tasks that seem to require a lot of very careful, precise insertion, a lot of high precision, but not necessarily tasks that we would naively think of as having multiple modes in the training data distribution. Okay. The second observation is, do we actually see any evidence of multimodality as we're doing learning, or from the policies that we learn? So we do 3 experiments here. So the first experiment, we take a couple of domains that are widely credited as being multimodal, and we visualize the action distribution. Moreover, we also color code the actions by their Q function, which is the measure of their return to go. So that, roughly speaking, the closer you are to dark red, the better the return is of that action. And what we see is not only is there no evident action multimodality at the chunk level, we also don't even see that the distributions have any structure relative to the rewards. So it's not like there's one mode of high reward, it's just all uniformly dispersed. Okay, but our eyes can be deceiving, and low-dimensional visualizations can also be deceiving, so that's not enough. In the second task, what we do is we study the inference procedure. So we compare using the flow model as it's trained, which is you sample noise from a Gaussian, and we compare that to sampling noise, which is 0. And unsurprisingly, the dip in performance is not that much, right? Because in robotics, you only care about one good action. But what might be a little bit more surprising is this experiment. So we now sample 64 noise seeds Z in parallel. For each of them, we execute the ODE and we compute its action. We now compute the average over the actions. So essentially, we're computing a Monte Carlo mean of this distribution at every step. And this is absolutely destroying any multimodality that might be present. And the performance drop is only 2%. Right? So there seems to be no loss if we actively kill the multimodality in the distribution we learn, basically saying that at least at inference time, preservation of multimodality doesn't seem to be necessary. And finally, we want to understand if we were to control our data so that our demonstrator were purely deterministic, would we still see a benefit from using a generative control policy? The answer is, under a controlled data collection with a deterministic neural network, the gap between flow and regression policies does narrow a bit, but we still see a statistically significant advantage to using flow-based modeling. Okay. So maybe stated otherwise, I think this all provides pretty compelling evidence that even if distributional learning might be possible, it's certainly not responsible for some of the benefits that we see. Right. Okay. So now what we try to do is say, okay, can we ablate away the distributional learning, but try to preserve some of the other qualities that flows have, and try to understand whether these are responsible for the performance. So to do this, we introduce what we call the minimal iterative policy, which is trying to capture the properties of stochasticity and iterative computation, but in the absence of distribution fitting. So the way that we do it is quite simple. We first train a policy that just simply fits actions via regression. And then we train a second policy, in practice they're actually shared as the same neural network, which tries to take in the state, take in a noised version of the action, and then again predict the clean action. So some form of one step of self-correction. And for inference, what we do is we just simply predict our first action, use that as a guess, and feed it to the second policy. This is called the minimal iterative policy, or MIP. Okay. And essentially all it's doing is we see the stochasticity injection, that comes in step 2. We see the supervised iterative computation, that comes because you're just doing 2 steps. So simple. So how well does MIP do? MIP, the performance of MIP is plotted in red, and that of flow is plotted in green or teal. And you can see that on many tasks, essentially MIP and flow are neck and neck. Oftentimes MIP might even do a little bit better. However, if you try to remove one or the other of these 2 conditions, right? So if you only try to keep stochasticity injection, but with no iterative computation, we get the method called straight flow, which doesn't really do much. And if you try to do only iterative computation without stochasticity, that doesn't work either. So it seems that this combination of things makes things work so well. So now we can ask ourselves, why would iterative computation be helpful? So let me give you one hypothesis. Imagine that I have a bunch of demonstrations, and in high dimensions, these are going to be sparse and somewhat separated. Okay. So one thing my policy could do is it could just smush them all together and learn some just distribution over all actions. And that would result in this multimodal policy learning in B2 that we observe over here. Right? But the thing my policy could also do, because we don't see multimodality, is instead learn how to separate between left and right really effectively and really quickly. So maybe we can imagine that if you do multi-step generation, you're just better able, you're more expressive in representing these fast switches from left to right. So why would you believe this? Well, deep neural networks are known to have higher Lipschitz constants. And we can think of a flow model maybe as a deep neural network where we're performing individual steps of a computation. So that's something that's very reasonable to believe. But it's wrong. So it actually turns out that if your policy doesn't learn multimodality, then it's not going to get additional expressivity in terms of Lipschitz constants from depth or from multiple steps. The reason is that typically if you're not multimodal, your distributions are what we call log concave. These are contractive. And log concavity implies that, in fact, like you're not too sensitive to the score functions you learn at every step. And this contractive behavior means that your Lipschitz constants don't grow much more in a flow model. In fact, oftentimes flow policies, if you just use a single noise seed, learn smoother functions than regression rather than more high Lipschitz ones. Okay. So this can't be the effect. So let me provide another tangent which might try to contextualize why flow models actually are doing better. And I'm going to compare it to a different data collection strategy and try to argue that flow models are capturing an inductive bias that are similar to what might emerge if we collected better data. So remember, in regular imitation learning, we take our expert data, and we learn policies that approximate the actions on the distribution of expert data. But we could also do something where we collect a little bit more data with exploration, right? So we could do noisy data collection, where we add noise to our actions. We then get clean expert actions at every state that we visit. So wherever we see a state, we record what the expert would have done without the noise added. And finally, we train our policy to imitate the clean expert, but under the distribution of noisy states, like this. Okay. So again, you're adding noise to collect new states to visit, you're recording the ground truth, and you're training to imitate the ground truth on noisy states. Now, it turns out that this data collection, even on unstable dynamical systems that are smooth, will provably guarantee imitation without compounding error with basically an optimal rate. Now, why does this happen? It turns out that if you inject noise into the action space, you excite what are called the controllable modes in the system. There's a thing for every trajectory. You can imagine a linear dynamical system following around it, and you excite what's called the controllability gradient around this system. And there's some magical linear algebra that you can use to show that if you excite the controllability gradient, you excite every direction that is potentially unstable and therefore susceptible to compounding error. And so this result does not require controllability of the system or anything. It just kind of works because there's this magical alignment between controllability and sensitivity to learning error. Okay. And this algorithm of adding noise is not very new. For example, the DART algorithm from Ken Goldsberg's group had done similar things. Here we just show that this is kind of theoretically grounded and in fact doesn't even require interactive data collection. Now I should mention as an aside for those of you that do train robot policies, I wouldn't recommend collecting data this way. And in fact, other kind of more semantic forms of correction seem to be much more important than this kind of thing. But it is at least a useful way to kind of conceptualize how we might collect data to overcome these instabilities. So this kind of data collection, this theorem motivates the following experiment. Let's actually compare how the policy would generalize when we train on regular expert data, but we evaluate on the noise data that we collect in this fashion. So imagine I have some distribution over actions as I move through state space. I'll call it the action manifold. And imagine that this is my expert action over here. Right? And so I'm learning to imitate this. Now what we're going to do is we're going to collect a bunch of trajectories that are close by perturbing the action variables. So we get some local approximation. And we can think about like these actions as spanning some linear subspace, which we'll call kind of the action manifold, the local tangent approximation to the action manifold. Okay. So now what we're going to do is evaluate two quantities. We're going to evaluate the generalization error, the L2 loss, how close this action was to this expert data. And we're also going to evaluate the off-manifold L2 or off-manifold error. So this measures not how close we are to these noisy actions. Rather, what it measures is how close we are to being in the span of the noisy of the states we would or the actions we'd reach if we added noise to the states. Right? So the reason you could think of this inductive bias as being useful in robotics is imagine an insertion task. Right? My policy might have error along the direction where I want to insert, but that's not so bad. What's bad is error that's normal to the direction I want to insert. Right? So somehow what we find is that flow-based policies seem to approximate some of the things that we really want from this form of data augmentation without doing the data augmentation itself, by doing this kind of projection. Okay. And again, it's kind of interesting to see that regression sometimes does better on validation loss, but worse on this projection metric. We also have a ton of toy experiments which validate this as well and kind of really dig into it. So again, this is kind of the key finding. It's that these GCPs, what they're really doing is they're exhibiting this lower off-manifold error on these noise trajectories. Okay. Now, why does this happen? We actually don't have a concrete theoretical explanation. The reason why is because, yes, you can prove that diffusion models map you to a manifold, but so too can you prove that if you train a regression model and all your actions lie in a low-dimensional manifold, the regression model will also learn the manifold. So to make this point clear, one would need to show that diffusion or generative models learn manifolds better than regression. And currently, I haven't seen anybody be able to establish this rigorously, but at least we have very strong experimental evidence of this phenomenon. And I can give kind of a conceptual picture for why you might imagine this happening. At every step, what you do is you kind of get one guess at the manifold. So you predict an action, you add a little bit of noise to move off of it, and then you have another attempt to predict the action to get back onto the manifold. And this process seems to be something that's quite useful. But I think making it rigorous remains an open problem. Okay. Right. And notice that this is quite different than expressivity, right? This is not that your generative model can represent more complicated functions. It's actually that it has a regularization effect, right? Which is kind of interesting. Right. So also, it turns out that stochasticity is really necessary here because the stochasticity kind of functions like the adding noise to your action space in the other thing. It basically removes distribution shift through the generation process. And of course, all this requires the iterative computation. But it's kind of the synergy between these two that seem to be essential. Cool. So I think this is kind of nice because we always thought that generative control policies were about distribution approximation, but it actually seems that they're about addressing some of these challenges associated with the control theoretic difficulties of learning from demonstration data, which I was kind of surprised to do. So for people who are more kind of practical in the audience, you might want to ask, should I be using the minimal iterative policy? So let me give an answer. Does it work with VLAs? Right? So the first thing someone at Pi asked me was, go train a droid data set and see if it works. Or go fine-tune a Pi with MIP. Does it work? The answer is yes. Right? So I don't think I have the droid data to share with you here, but it worked pretty well in the droid data. And indeed, if you fine-tune a Pi model on, say, some Libero tasks, it seems to outperform even flow models in some cases, which is kind of cool. Okay. The second question is, and again, this is single task fine-tuning. So for pre-training scale, I'll get to that. What about task diversity, right? So do you need flow models to have more diverse solutions to tasks? Turns out you don't even need to go to MIP for task diversity. Even a regression model can give you task diversity. So why is this? Because oftentimes what you care about in task diversity is diversity at the level of trajectories, not at the level of the per state action distribution. And even regression can provide a lot of this diversity, right? So people might complain, I don't get much exploration through my action model, but maybe you do at the level of your resets and all these other things. So my answer, should you use MIP? Not unless you need to. So let me tell you the advantages. If you want insightful ablations, we found it really useful. So if you think your flow model is now doing some weird multimodal thing, you want to test it, try to see if MIP works. If MIP works, maybe your flow model is not being multimodal. The other thing is, if you want a policy with really fast inference, at least in our experiments, it seemed that MIP performed much better than things like consistency models. So from our experiments, and in particular, MIP was a lot less sensitive to it seemed like medium proficiency data than these models, and sort of a lot better at high precision tasks than consistency models. The way that you can think about this is that if you have a very high precision task, all you really want to do is just correct your errors. Whereas if you have a consistency model, for the audience, a consistency model is one that basically tries to learn the integration of an ODE that you have in a flow into a one-step. And a consistency model is more about being faithful to the learned flow than about pushing you back to the action manifold, which is how MIP is directly trained. So we believe that probably these things are better as shortcut policies. But there are cons. I think at pre-training scale, there probably is some degree of multimodality, and that I suspect flows make much better pre-training objectives, if for the only reason that they have more steps of iterative computation. So I would not recommend pre-training with MIP. I would also say that flows are much more stable for RL fine-tuning for a range of reasons. One thing being that you get more plasticity if you have multiple steps of computation. You can also add more noise to your flow and get stability back to the manifold. So what I would say is, in that case, probably you want to use it for RL. But I think there is room to explore the capability of MIP as residual models, like people have been doing a lot of residual policy learning. There's also a lot of room to explore MIP as parameterizations of Q functions in RL. There's been a lot of work on flow-based critics. In my experience, I haven't been able to get those to work on very precise manipulation tasks, but it's entirely possible that a MIP-based critic might be able to do that. So if you want to use MIP, though, I think people have told me, oh, I've been running into issues using MIP. It doesn't work on my task. You have to email Xiaoyi. There are some subtleties, but I know he's been able to unstick people in the past. So if you're curious about it, you should email him. And I think actually on the Much Ado About Noising page, there is some like a quick start guide. But if you have questions, Xiaoyi will set you up. One other question I thought was quite interesting. I thought this would be the mechanism by which they were useful. They're not, but it's kind of a nice aside. You could think of other reasons why you might want to use a generative control policy to fit like a function, right? So what's kind of miraculous about this is that at the end of the day, flow models were discovered potentially as better ways to fit deterministic functions, right? Deterministic policies, but using distributional models. So why might you want to do this? Well, here's another reason. I know people in the audience are concerned or interested in uncertainty quantification. So imagine that I have a function that's very hard to fit. Here I've plotted the function y equals sine of 1 over x. Okay? So as I move towards the origin, I can no longer fit this with any neural network. The oscillations become infinitely rapid. So I can think about this as epistemic uncertainty just from the perspective that my neural network is unable to represent the function that I want to fit. Now, we can compare flow and regression models. And it turns out that with a fixed noise, z equals 0, the regression model and the flow model look similar. In fact, the flow model looks a little smoother. But the cool thing about flow models is that when you cannot fit the function, you get higher variance. So you essentially can convert epistemic uncertainty into aleatoric uncertainty. And I think this is a really nice property. I'm kind of working on with some theory students on understanding the extent to which this is possible. I don't know how much this will generalize in more interesting cases. But I think that maybe in problems where you have things like where you're doing like critic learning and reinforcement learning, or in low dimensions, this might be useful. For high dimensions, I would really look at Andrea Baici's work, who's been really interested in uncertainty quantification in diffusion models. I think that there are other considerations when you consider images, because images are so highly structured. And also, maybe another aside, just for those that aren't familiar with image diffusion, there's something very magical about how the denoising process and natural image, the distribution of frequencies in natural images seem to align. So this technology is like really overfit kind of to images, and so there are probably other things you can do there. Okay, so let me just kind of go through and conclude what we've learned and what we've established today. So this talk was kind of a control theoretic perspective, right? So what we try to do is show that continuous control imitation learning was fundamentally harder, or could be fundamentally more challenging than what we encountered in discrete settings like in language modeling. And as a consequence of this, we attributed the inflection point in sort of imitation-based robotics to basically two design decisions that inadvertently witnessed or inadvertently addressed the fundamental difficulties of imitation. These being the action chunking procedure, which works when the system is open loop stable, and the generative modeling procedure, which potentially makes things work better even under instability or high precision requirements via the action projection or the manifold projection mechanism. So again, we can kind of use this, I at least take this as evidence of the algorithmic Moravec's paradox kind of perspective that indeed learning from robot data is not fundamentally harder, but it is harder unless certain key algorithmic design decisions are taken into account. And upon figuring these out, scaling became unlocked. So now I kind of want to ask, we've talked a lot about control, what does remain hard about robotics? And I'm relatively new to robotics, and so you have yet to truly understand this. But what I would say is that maybe one perspective is maybe nothing if we get the data. I don't think this is quite right. So certainly there are challenges, right, for like broad world understanding, in-context learning, long horizon memory, robotic dexterity. I think these are still fundamental. But I think the way that I think about difficulty and data scaling is that there's this unfortunate correlation. Right? Because the tasks that have the most economic utility are often also the tasks we have to do the most often, or the tasks where we're most willing to pay to instrument the data. And so oftentimes, it becomes very easy to learn the tasks that we're most likely to raise money to solve because we have a lot of data or can pay for the data. Whereas a lot of academia, maybe we want to have happen here, right? Where we haven't yet convinced people that we want to scale the data, or we haven't convinced people that this is worth doing, or this is on the margins of our capability. It's a robot in space, or it's a nano factory or something. And kind of my bitter lesson is that at least in the short term, these tasks are always very cool for researchers, but they're not the things that are necessary for short-term commercialization. And so if you want to make short-term impact, oftentimes you can get away with much simpler or less interesting algorithmic interventions precisely because you're in the regime where it's economically viable to collect data. But I do think that in the long run, we're still very far from what we think of as an intelligent robot, in the sense that humans have this remarkable ability to learn rapidly from few-shot adaptation, or in novel or rare, or situations that have low action similarity between training data and novel actions. So my favorite example of this is the fact that orangutans can drive golf carts, right? It's really, really unbelievable. And in fact, you can ask a question, how many flops were used by the orangutan, or how many kilojoules were used? And if you were to compare that number of flops to what Waymo uses in pre-training, you'd be really embarrassed, right? Of course, orangutans have really strong inductive biases, navigation, 3D understanding. But this is all to say that I think we're very far away from a robot that can go and learn how to operate a new piece of machinery, right? So I think that puts things. Now the question is, it's probably still cheaper to have self-driving cars and Waymo instrumented. I'd rather have a Waymo than an orangutan Uber driver. But I do think that like there is still a lot of work to be done towards sort of agents in the world that are sort of physically, you know, intelligent. Maybe one last coda is, what can these insights tell us beyond robotics? So empirically, we know that this compounding error phenomena can also arise in any case where you have to execute the model back on itself. That could be in autoregressive language modeling and in generative modeling. And so sort of in some following up work, we're calling this the test time feedback phenomena, right? Where a model is used to make generations and it's fed back into itself through maybe a black box network. And so maybe we could ask ourselves, just like flow models were able to circumvent sort of the compounding error effect just without more data, but with a better inductive bias, maybe there exist tools from deep learning optimization that can ameliorate test time feedback in other domains beyond just robotics. Right? The things that exist over here, maybe, things, especially when data is scarce. So essentially, we've been working on a new family of optimization algorithms, depicted in the light blue compared to the baselines in light red. Just so you know, all the learning rates I'm depicting are tuned to optimize the baseline, not our method. And indeed, what we can see is that these optimizers do seem to benefit cases like robotics, improving the success rate, but also performance in language modeling and even in image generative modeling. And you might, if you actually were to look at the training curves, you would see that our optimizer and the true optimizer, or the baseline optimizer, are indistinguishable in terms of training loss, indistinguishable in terms of held out validation loss, but in terms of multi-step test time feedback, they seem to do much better. But unfortunately, that work isn't out yet, so you'll have to stay tuned. And thanks for having me. Cool. Yeah. Yes.
I had a question. You talked about the stability benefits of position control. I was wondering if you had any thoughts on extending generative policies to take more advantage of lower level control stack.
Yeah, I think this is just a data issue because I think you have so much data around, like if you have enough data of your same embodiment, that's going to generalize to all different kinds of tasks. So my sense is that as you scale data, you should actually be able to get rid of position control. In fact, I was talking to Chelsea Finn earlier, and I brought this up, and yeah, she was like, "Yeah, why don't we just try it at Pi?" Actually, she explained to me that her earliest work didn't use position control, like the early like mid 2010s Sergey Chelsea stuff just used torque level control. And I suspect that with the right data scaling, that should come back. Again, this is like kind of another perspective. Is a lot of these interventions, if like a VC had given us $10 billion to do robot data collection, maybe we would have not needed any of this stuff. But these were sort of the things that enabled us to kind of get off the ground at small scale. Yes?
When it comes to the intervention you did with the interpretation that when you train the full model, you have the iterative policy, like why that kind of maps you back to the expert manifold. I guess my first question is, why is this particularly different than just simply noising the observations during training?
Yes.
The second thing is, when you're like, would it be better because you're using the same network to kind of generate these noise steps, like the first step that you pick and make, and that's why it's kind of more in distribution of the learner rather than just adding noise to the expert demonstrations?
Yeah, so I guess there's exactly. So let me say there are a couple. One question is about adding noise to observation. So unfortunately, from image-rich observations, the right noise distribution to corrupt your observations, that's entirely unclear. The second thing is actually adding noise to observations has a really interesting theoretical effect, which is it basically causes you to learn from like the posterior over actions given uncertainty in your observation. It turns out this has like really cool theoretical properties, and I wrote a paper about this about like 2 years ago. It introduces something called like the replica distribution, which is inspired by replica symmetry in physics, but it's like not useful in actual robotics. Adding noise to your expert actions, that's just going to add more regression noise. So the reason that you want to add noise to the actions you do is because specifically you're not trying to combat generalized distribution shift. You're trying to, where's MIP? Here, where'd I put it? 1 second. You're not trying to combat generalized distribution shift. You're trying to combat the distribution shift under your own policy, right? You're trying to correct your own errors, and that's why you add noise to your own actions. Yeah.
And so that's why it's like the first step of the MIP, and you do like where you have the noise and kind of. You're saying
actually, wait, no. So we can add noise directly to expert actions. That's how we're training it. We're not, like during training, yeah. So the way to think of this is that like if your expert action is close enough to like your MIP, like if your MIP action first step is like within this like noise ball of the expert action, then basically adding noise to one or the other gives you the same distribution more or less.
Yeah, I guess my question is like, is the insight that because you're using the same network for both of your steps?
Oh yes.
Kind of get like.
Yeah, I see. So from what I understand, I think we can ablate away and use separate networks. The other thing is that basically we're still using, if you use the same network, we're using a time embedding, right? So these are different, like in practice you're using a time embedding, and the time embedding is like at t equals 0.9. So it very much separates these two things. So in principle, you can just learn two separate circuits. Maybe there is some shared representation learning, which is useful if you have pixels, but yeah, I don't think the networks are overly coupled. I think if you use exactly the same network, it does not work, right? Because you do want to learn a different mechanism for correcting than not correcting. The other thing is that also, like if you do the first step, your first step essentially has to condition on like zero action, and so it's hard to learn like the first action shot versus like the correction behavior. Those like end up being very different. Yeah. Sure. Other questions? Cool.
Speaker again.
Yeah, thanks so much.